Hello. In this lab, we conducted an experiment to observe Faraday's law in a falling magnet through an aluminum foil tube. So for our fundamental principles, we have our magnetic flux, which is just equal to B times n hat delta A. And if you were to take the derivative of that to find the change in magnetic flux over the change in time, then that would be this very long equation that we will be using later on in our code. And for Faraday's law, pretty much when you drop a magnet through a closed conducting loop, it generates an EMF within that loop. And so that EMF is just equal to the negative change in magnetic flux over change in time. So for an overview of our experiment, here is a video of one of the videos that I used to conduct the experiment. And so we determine the north and south ends of the bar magnet, and then drop the bar magnet through a roll of aluminum foil that's over 1 centimeter thick. In my case, it was about 1.6 centimeters. And then I repeated this 6 times and averaged the values of how long it took for the magnet to fall. And so when the north side was up, the average time was 1.3998 seconds, and when the south was up, then it was 1.29987 seconds. So there's a bit of a difference, but not too significant. And so for our computational model code, we have all of our physical constants and initializing a graph with velocity over time. And then creating the tube of aluminum foil, I just put in my length and width measurements from my actual tube of aluminum foil. And then we have numerical parameters that pretty much initializing conditions for our actual simulation. And then for creating the bar magnet, we have our mass is 0.023, which is just taken from the website I ordered it from. We have our magnitude of mu, which is magnitude of the magnetic dipole moment, which is 3.689. It's quite high compared to what I think it should be, which causes some issues that we'll see later on. And then visualizing the bar magnet, it's pretty much just a cylinder, and we calculate the magnetic dipole moment of the bar magnet and the mu hat. For our initial conditions, we start off the magnet at 0 velocity at time is equal to 0. And so we create a function to calculate the magnetic field of the bar magnet, which we just took from our Lab 3 code, and then we create a function to calculate the magnetic flux. And so pretty much all these find conditions that we put into our numerator and our denominator, which is pretty much that very long equation that we saw on our fundamental principle slide. And so this will get us the change in flux over the change in time. And so for our simulation loop, pretty much this is just saying, has the bar magnet entered the tube, has it not? And then we calculate our force of gravity, which is just negative mass times g, of course. And then we find basically our d flux dt using that function that we created earlier. And then for our ring current, it's just going to be d flux dt over the resistance of the ring. And then for the steps 5 and 6, pretty much we are calculating the magnitude of the force on the magnet. And then the overall force magnetic is just going to be what we just calculated in steps 5 and 6. And then our F net is just the F magnetic plus the force of gravity. And then we have our Newton's second law equation that just iterates through every time that this loop happens. And then we plot our velocity versus time pretty much. And then for our computational model, we actually got a time in tube of 17.377 seconds, which is far longer than it should be. So some of this could be attributed to human error in the experiment, maybe not dropping the magnet correctly, but more than likely it's because my mu mag from lab 3 was not perfect, which definitely affected the computational model. And when I adjusted this value to 1.2, I got a time of 1.844 seconds, which is much closer to what it looks like in the experiment. And so why couldn't we use a ferrous tube? Well, the magnetic force of the ferrous tube would be stronger than the force of gravity, so the magnet would just not fall. And so what happens to the magnet as it falls? It pretty much seemed to wiggle as it falls instead of just dropping straight down as it would when falling in free space. And so what if the resistivity of the conductor was as close as possible to 0? Well, the low resistivity would increase the quality of the conductor, increasing the magnetic force exerted on the falling magnet, so the magnet would fall slower. And so what if holes or slots were cut into the tube? Well, less material in the tube would exert a smaller magnetic force on the magnet, which would allow it to fall faster. So that's it for my presentation, and thank you for watching.